Okay, so welcome to this first edition, I think, of the IA fourth weekly seminar of this year, 2022. It's a pleasure to have today with us Dr. Seiji Fujimoto. Seiji is a Dawn Fellow at the Cosmic Dawn Center at the Niels Bohr Institute. He obtained his PhD from the University of Tokyo in 2019. And he was briefly then a postdoc and an ALMA project researcher in Tokyo before he moved to Denmark, to the Niels Bohr Institute, where he is right now. And he is going to talk about today about exploring the cold universe from obscure galactic nuclei, interstellar to circumgalactic media in galaxies at high redshift between 5 and 7. So whenever you are ready, Seiji, please take it away.
Okay, so hello everyone and Happy New Year. So I'm Seiji Fujimoto, and yeah, first of all, thanks to the organizer for providing me this great opportunity, and I really appreciate the kind introduction from Daniel. So yeah, I've never been to Crete, so it's a bit pity that we cannot see in person this time, but I hope some of you will be interested in our works or me after the talk today, and I hope we can see in person next time. Yeah, next time. So yeah, today I will talk about the cold universe, which means the fine-flat emission, especially from the very high redshift universe. But before my talk, because I guess many of you will be the first time to see me. So yeah, I'd like to start from my casual introduction a bit more. So yeah, so I was born in Kyoto, and yeah, as Tanyo nicely introduced, I got a PhD, got a bachelor, master, PhD in the University of Tokyo, and my supervisor was Masami Oji, and yeah, after a short postdoc with Akio Inoue, I moved to Cosmic Dawn Center about 2 years ago. So from last year, I also awarded about one what is called a sort of co-funding EU fellowship related to Marie Curie Foundation, so which makes me having 2 titles now. So my research interest is formation and evolution of the galaxy and the black hole in the early universe. So here is the list of the project which I'm currently involved with, especially using Subaru, HST, and ALMA, including a large project. And also I'm leading one JWST project as a PI, which I will explain the details later. So now I move on as a scientific introduction about my talk today. So from when I was a PhD student, I have been particularly interested in the cold side of the universe. So here shows 3 major energies coming from the universe. So the optical and microwave component called COB and CMB are already fully explained by hot stellar continuum and remnant of the Big Bang, respectively. So on the other hand, the central infrared component called CIB is thought to be thermal continuum emission from cold dust and fine-flat emission lines. But the origin of the CIB has not yet been fully resolved, despite its importance as one of the major contributors to the total radiation in the universe. So this indicates that there are still many unknown things in this other side of the universe. So my research scope is to explore the cold side of the universe by using latest facilities in the fine-flat wavelength regime. So in my talk today, I will highlight recent discoveries in the fine-flat side of the early universe from our latest works in a wide range of scales, from circumgalactic medium called CGM and interstellar medium ISM, and to the active galactic nucleus agent scale that we have recently published or submitted the papers. So now let's start from the CGM scale. So this illustrates the baryon cycling from the central galaxy to the CGM scale. In this baryon cycling, the CGM metal enrichment is caused by the feedback mechanism from the central galaxies. So investigating the metal enrichment around the early galaxy would be one of the helpful proofs to understand feedback mechanism, which regulates galaxy formation and evolution. So in the CGM-Scale observation in the early universe, it has been well known that there exists very extended Lyman alpha structure, what is called Lyman alpha halo. But the Lyman alpha emission only traces the neutral hydrogen, which gives no information about the metal. On the other hand, recent ALMA observations allow us to detect the dust and metal emission even from latitude beyond 6, which would be the good proof to study metal enrichment around the early galaxies. However, previous observations do not have enough sensitivity to investigate the diffuse emission extended even up to the CGM scale. So what we did at first was stacking. To carry out reliable stacking, we made our stacking sample from the object whose C+ line are individually detected in our original and archival data. So we set following criteria to select normal Sahuin galaxies at latitude over 5. And finally, we obtained 18 C+ lines detected sources with the star formation rate from 10 to 70 at latitude from 5 to 7, including 2 sources newly identified in our complete archival data analysis that are not reported in the previous study. So by using these sources, we perform the stacking. So we carry out the visibility-based stacking and obtain the final stacked visibility with a beautiful sampling like this. The total on-source time effectively reaches about 25 hours, which is one of the deepest data set targeting redshift 6 galaxies so far obtained. So now let's see the stacked images. So here shows the continuum stacking result averaged over 18 star-forming galaxies at redshift average like redshift around 6. So we obtain nearly 10 sigma level detection with the compact morphology. On the other hand, C+ line result is like this. So C+ line is also brightly detected at 20 sigma level, whose morphology clearly extended much more than the dust continuum. So even after masking the central area corresponding to the double size of the this ALMA beam, the extended emission is detected at the 9 sigma level in the aperture of the 10 kiloparsec scale radius. So this indicates that this extended morphology is not caused by the noise fluctuation. So here I also show the radial profile in the right panel. So because nearly 60% of our ALMA sample also has the deep HST H-band data, we carry out stacking also for the HST data corresponding to the less frame UV continuum. So performing the ALMA stacking only with the same sample used in the HST stacking, now we can fairly compare the spatial distribution of these 3 emissions. So this center panel figure shows the stacked HST map after smoothing to match the spatial resolution between ALMA and HST. And the less frame UV radial profile is now also shown in the right panel. Based on these figures, we find that C+ line is still extended more than both less frame UV and fine flat dust continuum, because this continuum emission traces the total star-forming region mostly corresponding to the galaxy distribution, galaxy size. This would indicate that C+ line is widely distributed even beyond the galaxy scale. Then the following 2 questions will be coming up. So how carbon was enriched in 10 kiloparsec, even 10 kiloparsec scale away from the central galaxy, and what powers the ionized carbon emissions, such as photonization, outflow, or inflow. So I would address this question from the first one. So there would be 2 possibilities to explain the metal in the CGM. So first would be there exists faint satellite galaxies, and second is past outflow activity, which I briefly explained in the introduction. To test these 2 possibilities, we evaluate the radial values of the total star formation rate, now evaluated thanks to the deep less frame UV and fine flat dust continuum stacking results, and check whether the ratio of C+ luminosity over star formation rate can be explained by faint low mass individual galaxies. So the right panel shows this ratio as a function of star formation rate. So the low mass galaxy results obtained in the local universe are plotted here, and our stacking result for redshift around 6 star forming galaxies are like this. So since the outer region has lower star formation rate values, this direction corresponds to the outer region. We find in the outer areas that the ratio cannot be explained by the low mass galaxies, suggesting that the first possibility would be ruled out. So the existence of the 10 kiloparsec scale extended structure, which is not caused by satellite galaxy, could be something like Lyman alpha halo. So we may be able to say we can call it C+ halo. So our result would be the evidence of the outflow remnants in the early galaxies, and so which will be good constraint on the feedback mechanism for early galaxy formation models. And in fact, we compare our result with 2 independent hydrodynamical zoom-in simulations. So we produce several cutout images for star-forming galaxies with the Halomus star formation rate and redshift similar to our ALMA sample, and perform the stacking in the same manner as observations. So in the right panel, the plots show the observational results and the model results for the continuum. Model results. Sorry, this data point is the observational data point, and the model results now draw in the line first for the continuum. And we find that both restaurant UV and fine-fed continuum are well reproduced in the models within the errors. However, we obtained C+ line model results like this. So the extended C+ line structure is not well reproduced, although one model reproduced the extended trend at least, but the large part of luminosity is still insufficient. So the existence of the C+ halo is challenging in the current galaxy formation models. To understand what is missed in the current models, it is also essential to address the second question, what powers the C+ emission? To do so, we need individual analysis rather than stacking. So this was why I joined and started working in the ALPINE team a few years ago. ALPINE is one of the large ALMA project program in Cycle 5, targeting in C+ line for over 100 main sequence galaxies at redshift around 4 to 6 in cosmos or good south field. The successful C+ line detection offers a variety of exciting studies, and in Olivier's paper, we did carefully classify the galaxy into 5 categories based on the morphology and the kinematics feature based on these large ancillary data sets taken in cosmos or good north field, and also this ALPINE data. So from this class 5 classification results, here we select only isolated ALPINE galaxy to remove potential effects on the halo emission from merging galaxies, and we set some of the essence threshold to obtain reliable results. So there are still 23 ALPINE galaxies. So based on this, we test the existence of the C+ halo around the individual galaxies. So left panel shows the reference UV continuum map taken from the HST after smooth to matte resolution with ALMA. So the red contour shows the C+ line taken from ALMA. So here shows the radial profile, radial surface brightness profile of the C+ line and test from UV continuum. To obtain quantitative result, we define the intensity of the extended emission beyond the smooth beam size up to the radius of 10 kiloparsec scale, and regarded the C+ halo as an object whose extended C+ emission is above 4 sigma level, while the extended UV continuum at the same area below 3 sigma level. We find that 7 out of 23 isolated ALPINE galaxies are classified as C+ halo objects, including these 2 objects. With upper limit of the rest frame UV and dust continuum, this previous figure already showed that such high C+ line ratio over star formation rate at the outer halo area cannot be explained by the low mass faint galaxies. So now we would be able to say that we are identifying the C+ halo individually. Thanks to this individual based approach, we obtain some hints for what gives a rise C+ emission in the extended structure. So here presents one C+ halo object clearly showing its rotation feature beyond 10 kiloparsec scale, and its rotation axis has a good agreement with the rest frame UV measure axis. So what we performed here is the realistic 3D rotation modeling. So here the right panel is the best fit momentum 1 velocity weighted map. So first of all, we obtained the effective radius of this rotating C+ gas disk is around 4 kiloparsec scale, which is about 4 times larger than rest frame UV disk. So we might be witnessing the kinematics of the C+ halo, or let's say a large gas disk connecting and co-rotating with the central galaxy disk. Interestingly, when we take a look at the residual map, we identify a symmetric feature perpendicular to the main disk. So this may indicate that we are also observing the ongoing biconical outflow, such like in the famous picture of M82. So the second case is one of the C+ halo object also shows an extended structure in the dust continuum. Since the carbon exists in the CGM scale, it might be natural that the dust is also there. But once after dust is pushed away from the galaxy, it will soon become cold, which would be very hard to be detected. But the extended dust continuum might be detected in some of the cases where this extended dust is heated by some mechanism or energetic process, such like outflow. Indeed, this C+ and dust halo object shows one of the highest Lyman alpha velocity offset from the Lyman alpha velocity offset, as well as the Lyman alpha equivalent width value among the C+ halo object, even with the existence of this large amount of dust. So some strong kinematics or energetic process like outflow may help the Lyman alpha photon successfully escape from the system. So in both cases, we might be observing the hint of the ongoing outflow. And also, interestingly, the similar evidence of the ongoing outflow has been also reported in a recent ALMA study. So in this study with a deep high resolution ALMA follow-up for a main sequence galaxy at redshift 5.5, first of all, the extended C+ line structure is confirmed around this individual galaxy as well. And also the spatially resolved aperture analysis for the C+ line spectrum shows the broad wing feature, which is well known as the outflow signature in the local universe, whereas also finds that this broad wing feature only appears along the minor axis of the galaxy. So this also resembles to the picture of the biconical outflow. So the extended C+ halo structure as well as the ongoing outflow feature have been getting to be identified in individual galaxies from multiple point of views. So here is a summary of the CGM scale. So we discover of 10 to 15 kiloparsec scale C+ halo statistically and individually, which would be the evidence of the outflow remnant and challenging current galaxy formation models, where a potential ongoing outflow feature have been also reported. So the next is ISM scale studies. So this picture is taken from the local universe, and some simulation snapshots for different elements of the galaxy are also shown in the left. There would be many reasons, but the ISM scale study is also very important because the galaxy evolution is regulated by several key mechanisms taking place in the ISM, such as clamp and disk formation, stellar feedback, and mass building via star formation and mergers. And as we saw in a few slides before, these mechanisms are also tightly related to the CGM scale by baryon cycle. So the difficulty is that achieving the subkiloparsec scale spatial resolution and requires sensitivity to resolve these ISM scale structure, especially at high latitude universe. To overcome such difficulties, an effective approach would be the gravitational lensing. So I started to work on this unique suballunar lensed galaxy found at redshift 7.1. So the dust continuum detection is reported in Watson et al. From Nature in 2015, and the follow-up ALMA spectroscopy has successfully detected the bright C+ and O3 emission from this galaxy. So after moving to Dawn, since the PI of this team is one of our Dawn colleagues, I had communicated with him, and from the last summer, I have been working with a student, Horst Akins, to achieve an unprecedented ISM scale study of this project. So the scope is subkiloparsec scale detail 2-dimensional and 3-dimensional structures of the multi-phase gases by utilizing these bright emission lines. So here is a multi-phase gas structure and the underlying continuum obtained with ALMA. I'd like to mention that this is one of the most rich ALMA datasets for studying high latitude galaxy, especially at epoch of reionization. For example, more than 10 hours of ALMA observing time is invested just for this C+ line and underlying dust continuum data. So thanks to this rich data, all emissions are detected with high significance levels, which allow us to perform a secure morphological study. To perform a fair comparison, we produce these maps in the same resolution where the HST map is smooth to match the resolution with ALMA again. But still, the subkiloparsec scale spatial resolution is achieved in the source plane that are summarized in this bottom panel. So the middle panel shows what is called visibility, where the UV distance corresponds to the antenna distance. So longer distance is comparable to very high spatial resolution. If the structure is not resolved, the amplitude shouldn't be changed. So it should be constant in that case. But this, when we observe this kind of decreasing shape as a function of the UV distance, then this means that structure is spatially resolved. And in this way, we obtain the fine FWHM size of something like 1 arc-second scale for these emissions. However, we find that only the C+ line emission has steep flux enhancement at the shortest baseline regime, which corresponds to a spatially extended structure with the FWHM size is something like 8 arc-second scale. So this confirms the existence of the secondary extended C+ halo component around a sub-Elster, even sub-Elster galaxy at redshift 7. To understand their intrinsic morphology, we also compare their radial profiles in the source plane after the lens correction. So we find that O3 and the UV continuum are similarly compact, while C+ line is extended up to a radius of 12 kiloparsec scale. This confirms the existence of the 10 kiloparsec scale C+ halo even around sub-Elster galaxy at redshift 7.1, also in the image plane analysis. Interestingly, when we derive the radial profile of the dust continuum, we also find this could also be extended similar to C+ line despite its large error burst. The extended dust structure reminds us one of the ALPINE galaxies showing both C+ and dust continuum similarly extended. So the extended dust structure might sometimes happen, or as I mentioned before, this might be a natural consequence of the existence of the C+ halo. So this means that if the carbon is extended, it might be natural that dust also exists there. And here, one of the deepest ALMA data with the gravitational lensing support might allow us to capture it. Anyway, in addition to the radial profile analysis, we also evaluate the morphology via the non-parametric analysis using Gini coefficient. So Gini coefficient represents the mean of the absolute difference among all pixel values across the galaxy, where high and low values corresponding to high and lowly concentrated morphology. So some of the examples are shown here. So we find that Gini coefficient suggests that C+ is smoothly distributed, while O3 and UV is highly concentrated, or this may indicate having a clumpy morphology. So interestingly, we also find the difference in the dust continuum against the wavelengths. So the shorter wavelengths, generally tracing the hotter dust component, has more clumpy morphology close to the O3 and less thin UV continuum. So this may indicate the differential distribution of the dust temperature within a galaxy. So we further analyze spatially resolved dust temperature map. So first, we reduce all available data for this object, the latest band 3, 6, 7, and even 9 ALMA data, setting the same aperture and derive the best fit fine-field SED in the spatially integrated manner first. So this produces consistent result with previous estimate, although previous study only used much smaller number of ALMA bands. And so then we fix the spectral index beta and derive the pixel by pixel best fit dust temperature value shown in the right panel. Since these two peaks at the edge are corresponding to the very large uncertainty areas, we ignore these very noisy peaks. And then we find that a gradient of the dust temperature up to a radius of 5 kiloparsec scale. So importantly, our results suggest that this outskirt region gets close to the CMB temperature. Since what we observe in general is the contrast from the background emission, so if the temperature is close to CMB, in principle, we cannot detect the emission. So the possible explanation of the extended dust structure which is not usually observed, could be like the dust is also extended similar to carbon, but the cold dust away from the galaxy center is embedded in the CMB and thus difficult to be seen in general. So the great resolution and sensitivity also allow us to search for the broad wing outflow features in both O3 and C+ emission lines. So here showed both spectra produced from the highest star formation surface density region in the system with the same aperture. First, we find that the different line profile between O3 and C+, where C+ is wider, which would be explained by the extended C+ line structure also along the line of sight. Second, and more importantly, we find significant residual signals only in O3 line spectra after subtracting the single Gaussian profile, suggesting that the presence of outflow, but this outflow gas might be dominated by the ionized gas. So from the presence of the C+ halo and the O3 outflow, a coherent picture would be like the outflowing gas is dominated by ionized gas at the first launching phase, but through the gas cooling process, the cool carbon gas halo starts to appear surrounding the galaxy. Of course, this scenario largely depends on the cooling timescale, which is regulated by gas density, metallicity, and multi-phase gas outflowing gas structure. So further investigation will be required in follow-up studies, but I'd like to tell you that we are well ready for further detailed analysis for this kind of topic. So let me explain this discovery. So in the last few slides, I demonstrated the power of the gravitational lensing. And in this context, I'm also working in ALMA lensing cluster survey, which is another ALMA large program to perform homogeneous 1 millimeter mapping towards 33 massive lensing clusters. So thanks to the unique parameter space explored by this survey, we recently discovered a strongly lensed multiply image the C+ emission line from let's choose 6 Lyman-Blake galaxy. So remarkably, the magnification factor of this source reaches around 20, or even beyond 100, which makes them the brightest object so far known at redshift beyond 6, but still intrinsically very faint sub-L-star galaxy. So this object will be a unique laboratory to investigate the typical galaxy property, even at redshift 6 in great detail. And actually, our proposed JWST program is accepted in GO Cycle 1. So the observation design and scopes are summarized here. So we will observe the brightest multiple images with near-cam and near-spec IFU targeting the key optical emission lines and underlying continuum. So there are three major scopes. So first is the detailed structure of the galaxy down to 20 to 80 parsec resolution scale in the source plane, which will securely resolve even the individual star forming clumps that are hinted by the current HST maps. And second is the internal physical properties such as BPT, electron density, and metallicity gradient in the spatially resolved manner. And the last is a detailed kinematics from ISM to CGM scales, including the motion of the individual clumps in falling or outflowing, and also rotation curve of the host galaxy, and the testing if there is a drop in the rotation curve at outer area, which will be a strong constraint of the dark matter halo concentration already starting around the typical galaxy at redshift 6 or not. But the exciting fact is that we were also awarded a total of 60 hours of deep ALMA follow-up for this strongly lensed system. So we will observe almost all key fine-felt emission lines as well as underlying continuum, which allow us to map out PDR gas distributions, detailed kinematics of the cold ISM gases, and accurate gas and dust mass estimates, and spatially resolved dust temperature and metallicity measurements. So combining these exciting data sets and the strong lensing effect, we will address the full characterization of early galaxy assembly, including a large variety of topics from the chemical abundance to the concentration of the dark matter down to 100 parsec scale at the 6. So this panchromatic ISM analysis will also help us to comprehensively understand the multi-phase outflow mechanism and the origin of the C+ halo. So here is a summary of the ISM scale part. So ALMA and gravitational lensing is a powerful approach showing the different 3D distributions between O3 and C+. So the dust temperature decreases towards the outer area, indicating that extended dust continuum could be embedded in the CMB. And we find the broad wing feature only in O3, indicating that outflowing gas could be dominated by the ionized gas emission. And the 100 parsec scale panchromatic ISM view will be further investigated with JWST and ALMA deep follow-up. So here is a summary of today's talk. So I highlight our recent works in the fine-felt side of early universe from the CGM, ISM, and the AGN scales. So first is a discovery of the 10 kiloparsec scale C+ halo, which is the direct evidence of outflow remnants and challenging the current galaxy formation models. So second is the discovery of the strongly dense sub-L-star galaxy at redshift 6 to 7, showing different 2D and 3-dimensional distribution of multi-phase components, suggesting that the cooling of the ionized gas outflow from the C+ halo. And the last is the discovery of the least luminous, most distant red quasar in the center of Kuznets field, which would be the first case of the young transition phase red quasar forming in a dust enshrouded starburst at redshift 7.2, suggesting the direct progenitor of luminous quasar at later epoch. So the final remark is that more than 100 hours of the PI data of ALMA, NOEMA, VLA, VLT, CAKE, and Subaru will be delivered in coming months or year, as listed below in different or relevant projects that I couldn't explain during my talk today. So I hope I can have another opportunity to give a talk about this exciting project as well in the near future, hopefully. in person next time. So yeah, thank you. That's it. Thank you for listening, and happy to take questions.
Thank you very much, Seiji. Let's see if anyone in the audience have any question. Vasilis, I think.
It's a great talk, Seiji. It was very informative. I was just wondering a couple of things. You discuss about the extent of the C+,
yeah,
right? And it appears that it's more extended than the dust continuum. But for local galaxies, we sort of like know that C+ in general sort of like globally correlates with regions where star formation takes place, and often when we see star formation, you have other tracers like PAH emission, etc., that you also has been detected in local outflows. So I was wondering, since star formation also associated with CO emission, and in particular, not necessarily dense CO, right? But because this is, are there any efforts to see whether you can detect redshifted CO 1 to 0, for example, or 2 to 1 using JWST or something like that?
Yeah, I totally agree that the CO 1 to 0 would be the best to further test the existence of this kind of cold gas halo, and would be CO measurement would provide us the mass estimate for this kind of extended molecular gas. But yeah, unfortunately, VLA, to address this redshift, we need VLA. But yeah, JWST doesn't have sufficient sensitivity to detect this kind of faint diffuse emission. But yeah, last year I contributed to write up some science notes for the next generation VLA. And when I did some simulation analysis, I confirmed that energy VLA is actually feasible to detect this kind of extended CO 1 to 0 or 2 to 1 emission. So yeah, when the next generation VLA starts, yeah, it will be one of the interesting science. But the other possibility would be C1 emission. So one of our own colleagues, Francesco Valentino, observed 40s or 70s of the redshift 1 or 2-ish main-thick normal star-forming galaxies observed with ALMA targeting C1 emission. So yeah, recently it is also well known that C1 is also good tracer for molecular gas. And so yeah, although we haven't yet tried, but if we stack this C1 data, again, we might be able to see the diffuse C1 gas distribution from those ALMA data.
And if we wanted to only restrict ourselves to searching for star formation, do you think JWST would be able to detect something like that, like redshifted H alpha in those regions, or other near infrared hydrogen recombination line, a bracket line, for example?
Yeah, actually, one of my goal in the JWST program is to see if the H alpha emission is also very extended or not. So yeah, of course, if the cool gas is dominated, so this C+ emission is originally produced from the, if this extended C+ emission is coming from the PDL, this cool gas region, then ionized gas might be not so extended, then H alpha might not be such extended. But but I know some of the zoom-in simulation result for such IRE galaxy actually in some simulation case suggests H alpha also extended. So yeah, JWST would be also one helpful proof to see if this kind of diffuse emission extended. But I remember that not only star-forming galaxy, quasar would be also interesting to see if this kind of emission exists around.
Because in general, it may be interesting to see this topic that Tanya is also very interested in, whether how closely associated C+ is with the star formation in general, right? And just one last thing, if you show your slide 31, where you were comparing your interesting source with R220 and quasar. I was just naively, I was wondering, I thought 31. Sorry, well, you had the SEDs.
SED, okay, got it.
Yeah.
This one.
That one. For example, if you were, when I see it, right, I mean, you were comparing and you were saying, okay, I have a dust enshrouded starburst, and then I have a quasar who is a bit warmer, right, than the starburst. So I was wondering if you were to put a simple Seyfert-1 galaxy, SED, would it resemble your red,
So yeah, actually we try to
thinking that local Lyric SED looks like a high redshift ULYRICs, right? Would a local Seyfert-1 resemble your galaxies, right?
So yeah, actually we try to just a full SED fitting only using star forming galaxy templates, but the most difficulty was taking place to reproduce 24 micron mixed data, so corresponding to reference 3 micron. Although we tried a lot, but we couldn't reproduce this mid-infrared emission only with the star forming galaxy template. So, and another point of view is this point source structure seen in the all HSD band. So actually, we run the GalFit, and the upper limit we obtain would be something like 60 parsec effective radius. So of course, we might not even how to say. So we actually calculate the surface density of UV luminosity based on this upper limit of the size. In that case, and if we assume the UV luminosity all coming from star forming activity, then the such surface density is 2 or 3 decks higher than any other known objects so far at redshift, at the high redshift. So we think that the interpretation of the red quasar with dusty starburst would be most reasonable.
Okay, thank you very much.
Thank you.
Great talk.
I don't know if there is any more questions. If not, I have a couple. The first one is related to the first question from Vasilis, related to the extent of the C+, and the fact that there is not that much extended emission of dust at those scales, and it relates also to your point. I think it was in the ISM section that at larger scales you may be sampling, or the average temperature of the dust would approach the CMB. So, I mean, it would be a very weird configuration of the phases, but I mean, if you think that dust at those temperatures would become effectively undetectable, but it doesn't mean that it's not there. It's still there, but we cannot see it. Would it be any? There would be. I don't know if would there be any way that you in fact would have some obscured star formation there, but we cannot see it. So still, there would be the possibility that that C+ is still powered by star formation and not by outflows.
Yeah,
it's difficult to test, but
but yeah, thank you for bringing up that possibility. I think one solution will be the JWST data, because JWST allow us to see the rest frame optical emission up to this CGM scale, at this, even at this redshift. So yeah, of course, young, but yeah, if some stars there, I hope it can be also observed in the rest of optical. And but one important point will be, if we would like to assume all these extended C+ emission caused by fully obscure dust, dusty obscure star activity, then the obscured fraction as a function of radius will be, how to say, 100% at the outer galaxy region, but the central area is much less. Then, how to say, in the context of the galaxy formation, it might be not usual, opposite from what people usually expect. So but of course, no one can give the perfect answer here, but but this is my understanding.
No, I completely agree. That's why I said like weird configuration of phases, right? But on the other hand, I mean, it would have to be called dust. It's not that, I mean, when we think about dust, we think about, oh, a starburst, right? But there could be low-level star formation that, or not so recent, some A star hitting that could hit, the dust up to like a 20 Kelvin, say, and you would still have some star formation associated to it. Okay, it wouldn't be like so recent, but at this epochs, maybe redshift 7 is having older stars is not highly likely. But I don't know, I was wondering just about that possibility, that maybe low-level star formation there.
But if low-level star formation, then, this time we also stack the HST data, then, and very deep HST data stacking also achieved. So we got the strong upper limit also from the rest frame UV. So if low level star formation and the obscured fraction is not 100%, then we may expect a very faint rest frame UV detection at the outer area, but based on this upper limit, the ratio couldn't. So, but
I mean, it's very well, extremely tentative, since the uncertainties don't allow it, right? But it looks like the slope of the UV in that spatial profile could be slightly
diffuse. Right.
So the contrast between the ratio of C+ to UV, not necessarily a star formation from IR, could track each other better. But I mean, it's deeper observations are needed for sure. Every tracer.
So I totally agree with your point, and thank you for bringing this up there. So although this time I often call it C+ halo, but I totally agree that we still not sure what we should call this. And I know that some of the people call this is just a extended galaxy disk, so not the independent halo. But we still not sure. But the important point that in any case, we at least could say that there exists some very extended something. So
definitely.
and in the current galaxy formation model, it cannot be reproduced. So I think whatever interpretation is, it would be the important point.
That was the other question I had. I mean, it's difficult to separate what is the, I mean, unless you have another traces like a stellar component, right?
Yeah.
It's difficult to separate what is the gas associated to the galaxy itself or to the circumgalactic medium.
Yeah.
So it's a. Is there? I saw that in your JWST proposal, you didn't ask for MIRI imaging for the.
Yes, I only asked the near spec IFU and the near cam imaging. Yeah.
Yeah, because I mean, in terms of stellar masses, having rest frame 1.6 micron image would help a lot to constrain where the stars are.
So in that case, yeah, we will get the rest frame optical continuum even with the near cam. So I hope this rest frame optical near cam imaging will be helpful a lot. But do you think it's still insufficient?
I mean, I guess if you, from the 4.5 micron, you get, this is redshift 6, right?
Yeah.
So it's,
I think it's corresponding to, still, okay.
Yeah, still, I think it's a short wavelength enough that you are mapping, well, you are more associated, that the luminosity comes from young stars that scale more with age rather than mass. So, but maybe with the full SED fitting, it's enough. I really don't.
Okay, so yeah, I hope in addition to the full HST band, and yeah, this additional near cam broadband and performing the full SED analysis may, give the answer.
Let's say 7,000 angstroms. The approach is to be mass dominated, but not yet. I mean, to be mass dominated, better observations are longer than one micron. Yeah.
Okay, so we think about the cycle 2 proposal.
Yeah.
Thank you.
Okay. I don't know if we have any other question. Okay. I don't think so. So if not, I will stop the recording right now. Okay. Thank you, Seiji, for joining us for the seminar today.
Thank you very much for inviting me, and hopefully see you in September.
Exactly. See you in person soon enough.
Thank you very much for your time. It was a
Thank you.
Thank you.
Thank you.
Thank you so much. So bye-bye.
Bye-bye.